Hey everyone, you've seen the movie, right? The rogue genius in some basement whipping up a nuke? Well, today we're gonna absolutely tear that idea apart. And not with secret documents, but with something way more powerful. Cold, hard math and physics. Let's dive in. Yeah, this quote right here, this is what we're all about today. That idea that someone can just build a nuke, it's not just a little wrong. It's a deep, fundamental misunderstanding of, well, everything. Physics, engineering, the universe itself. So let's start dismantling that lie, piece by impossible piece.
Okay, so here's the game plan. We'll start with the Hollywood myth. Then we're going to hit 3 total showstoppers. First, the material. Second, the perfect squeeze. And third, the race to not fizzle out. And at the end, we'll see how it all adds up to what I'm calling the wall of impossibility. All right, first up, the myth itself. You know the scene, the lone wolf, some stolen stuff, a ticking clock in a dark basement. It makes for a great action movie for sure, but for physics, it's just awful. Look, this isn't about some secret recipe you can find online. It's about the pure, unfiltered logic of why this is a complete non-starter from the get-go. We're talking about a thermodynamic nightmare. The universe itself is basically fighting you at every single step with the insane amount of energy and precision it demands. So yeah, it's not just hard, it's pretty much physically impossible. Which brings us to our first huge, massive failure point. Forget the engineering for a second. Before you can even think about building anything, you need the right stuff. And right here, this is where the whole fantasy just completely falls apart. So just look at the scale of this problem. When a bad guy in a movie steals uranium, what they've actually got is this. Almost all of it, 99.3%, is completely useless U-238. The magic ingredient, the only part that actually works, U-235, is, wait for it, less than 1%, 0.7%. It's not a needle in a haystack. It's a needle in a whole planet of haystacks. And this is the key thing you gotta get, that U-238, the stuff you have tons of, it's totally inert. It does nothing for a chain reaction. The source material put it perfectly. Trying to use it is like trying to start a bonfire with wet spaghetti. It's just not gonna happen. Only the U-235 works, and nature just doesn't give you much of it at all. Oh, but it gets so much worse. You don't just have to find that tiny 0.7%. No. For this to work, you have to purify it, you have to enrich it, all the way up to 90%. 90. You have to somehow take that tiny little sliver and turn it into almost the whole thing. So how on earth do you even do that? Well, it's not with a chemistry set in your garage, I can tell you that. First, you have to take solid uranium and turn it into this ridiculously toxic, supercorrosive gas. Then, you have to pipe that gas into thousands of centrifuges spinning at supersonic speeds just to slowly, and I mean slowly, separate atoms that have a mass difference of less than a single percent. It's an industrial process on a scale that is just mind-boggling. So yeah, this is the reality check. We're talking thousands of perfectly balanced rotors, all spinning together in a building the size of a city block. If just one of them wobbles, the whole thing can literally shatter. This isn't a weekend project. This needs the money and the industrial power of an entire country. The electricity bill alone would be insane, like powering a small city. For one person? No way. Absolutely out of the question. Okay, fine. Let's just pretend. Let's say some magical wizard just hands you a perfect, glowing sphere of weapons-grade material. Awesome. Congrats. You've just solved the first impossible problem, only to run smack into an even harder one. How do you actually make it go boom? And this right here is the big engineering puzzle. You can't just, hit it with a hammer. To make this thing work, you have to crush a solid sphere of metal with just unimaginable force. And not just crush it, you have to do it perfectly, evenly, from every single direction, all at the exact same instant. So how you do that? The answer is something called implosion geometry, and it is wild. It's this beautiful, brutal art of using perfectly shaped explosives. Some burn fast, some burn slow, and what they do is act like a lens for an explosion. Instead of blowing out, they focus all that force inward to create a perfect, crushing sphere of pressure. It's fluid dynamics on a level that's just, it's almost magic. And the timing? The timing has to be perfect. Absolutely brutal. Every single one of those explosives has to detonate within 1/1,000,000th of a second of each other. Let that sink in. Not a millisecond, a microsecond. A blink of an eye is an eternity compared to this. If you're off by even a tiny fraction,
the whole thing is a bust. Why? Because if that shockwave isn't perfectly symmetrical, if one side pushes even a fraction of a second early, you don't get a perfect squeeze. The core, this is a solid piece of metal, remember. It just deforms. It squirts out the side. And this quote from the source material is just perfect. It's like toothpaste getting squeezed out of a tube you stepped on. You just get a messy, expensive dud. No boom. And that brings us to the final hurdle, the grand finale of failure. Because even if you got the magic material and you somehow engineered a perfect implosion, you still have to win a race against physics itself that's over in nanoseconds. So here's the conflict happening at the very core of this thing. The second the chain reaction starts, it creates this insane energy that is trying to blow the whole device apart. We'll call that mechanical disassembly. At the very same time, the chain reaction, the neutron multiplication, has to finish its job before the bomb rips itself to shreds. It is the ultimate race against time, and it's over in billions of a second. And if you lose that race, if the core blows apart just a little too soon, the chain reaction just stops. The material isn't dense enough anymore, the neutrons just fly off into nowhere, and the whole thing dies. The official term for this is a fizzle, and it is the biggest anticlimax imaginable. All that work for what amounts to a messy radioactive pop instead of a bang. So let's pull all of this together. It becomes pretty clear that this whole thing isn't about finding some secret blueprint on the dark web. It's about trying to smash through a series of completely separate, totally insurmountable walls of physics and engineering. And this is the big takeaway. Look at this list. Every single one of these is a complete showstopper by itself. The fact you can't get the right atoms, the need for city-sized factory, the insane nanosecond precision required, the extreme temperatures and pressures, and just the brutal, unforgiving laws of physics. Any one of these makes it impossible. But all of them together, that's what we're calling the wall of impossibility. Which leaves us with one final thought. The universe is, well, it's brutally honest. It plays by very strict rules, and it really doesn't care if you get the math wrong. Just think about the brainpower it takes to even understand why this is impossible. It's immense, so it makes you wonder, what actual real-world problems could we solve if we applied that same level of intense focus and that same respect for the fundamental laws of nature? Something to think about. Thanks for joining me.